Good morning, everyone. My name is Michael Monette, technical product expert for Eddyfi, and today we're going to go and do a new coffee break. This week we're going to talk about time reversal, how to simplify your inspection of varying geometries with UT. So when we're talking about time reversal, there's a few inspection challenges that we need to take in mind and why we developed the tool and where we're going to use it. Especially in the aerospace industry, for example, the inspection of composite parts it's often complicated due to its varying geometry. You can have long, flat parts, but they can bend, they can twist, they can have some curvature to them. And 100% coverage, well, it requires inspection of convex and concave curves due to the complex geometry of the parts we're looking at. And usually a fully motorized 6-axis robot could be used to keep fully following the surface, but that's really expensive, takes a lot of space, it's long to set up, and breaks can happen just about any day with those fully complex motorized system. So at ZTech, what we did is we developed what we call time reversal. And time reversal was made to be able to replace expensive robots in complex inspection systems, really using only time reversal to adapt to those varying geometry. So we replace those really complex and expensive solutions using either a Topaz 32, a quartz, or a zircon phased array unit with the time reversal option, and some immersion adapted phased array probes with the Ultravision software to run everything for an efficient setup, good data recording and data analysis, and of course, reporting directly in that software. So that's the solution we recommend. And why do we recommend time reversal actually? Well, time reversal, it's used when the inspection of parts have changing geometry. So for example, there's a bend in the structure of a wing, for example, for an airplane. Well, the probe needs to be perpendicular to the surface all the time. Otherwise, the sound is going to bounce off and you're not going to get a 0-degree inspection. So if you don't have those probes perpendicular to the surface at all times, it makes the inspection really difficult, and it requires a complex mechanical setup. However, when you're using time reversal, well, it adapts the focusing as we're going live and adapts the beam itself to dynamically compensate for that geometry variation and always shoots the beam perpendicular to the surface. So it corrects misalignment of the probe angle with relation to the component, also corrects the water column changes if it goes up or down, if it changes height, if it changes angle between the probe and the component surface, and it will also adapt the UT beam characteristics to be able to compensate for component surface geometry for either concave or curves, for bends and things like that. How does it actually work? Well, there's the basic principle of time reversal is pretty simple. It's done in a 2-time process. So the first step is actually to fire a beam. And once that beam hits the material, it comes back at a certain angle or a certain profile, reflecting the geometry. And then we calculate the correct delays to adapt for that geometry or that angle or whatever. And then we're able to shoot with a straight beam, so that when we actually shoot for a flaw, for example, the beam ends up fully perpendicular to the surface and comes back with that flaw perpendicular to the surface once again. That also works on curved surfaces, like I'm showing right here, where we have a curved surfaces. We first shoot a straight beam, it comes back curved. We're able to calculate the correct delays to apply for a flat beam. And with those delays, we're actually able to find a flaw by shooting a beam that is fully perpendicular to that curved surface and comes back with the right profile. This can also be applied to non-linear curves, for example. For example, in this case, we have a specimen that goes from flat to curve to flat to curve. and we're actually able to compensate for it as well by using the same technique. So it's done in real time. You could use multiple iterations. In this case, I'm only showing one, but I could use multiple iterations to try and perfect my beam as much as possible when I'm firing, up to 9 iterations of time reversal if necessary to get a better profile. So how does it work? Well, it works on one of our 3 legacy phased array units, either the Topaz 32, which is a powerful portable phased array unit that has the onboard software of UltraVision Touch that can be run directly from the unit itself, so it makes a good portable solution. You also have the Quartz, which is optimized for inline inspections. It comes with directly 2 phased array connectors on the instrument, and it has parallel firing for optimized speed inspection. And finally, there's also the Zircon, which is a brilliant phased array unit, which is rugged for harsh environments. It's battery operated, but needs to be controlled from a computer. So those are the 3 units that can run time reversal on them. So there's some limitations, however, for time reversal. So those are the things you got to keep in mind when we're talking about time reversal inspection. So it is limited to 0-degree linear inspection. That's because we're correcting for geometry, but we're correcting for the surface geometry. So we're always going to target at a flat beam with respect to that geometry. So with regards to that, we're limited to a 0-degree inspection. We're able to correct for flat or for parabolas. So 1st and 2nd degree equations are able to be solved, but not more than that. So that's all being done in the firmware. So it's really where the limitations come. We can work in groups of 32 elements. So up to 4 groups of 32 elements with time reversal each, or 2 groups of 64 at the same time, no problem. If needed, we could always daisy chain multiple instruments together and then grow up. But for a single instrument, it's up to 4 groups of 32 or 2 groups of 64. And when we're using time reversal, it replaces any wedge delay. So it's better used with a synchronization gate that's going to that's going to set the start of your A scan to a certain position and not use, for example, a known column water height. It's going to be able to change throughout. So we're using the synchro gate to correct for that changes in water height of the water column. Typically, there's a few common cases that we're going to look at. Long, mostly flat parts that could twist or bend along the length. Specimens that are curved along the primary axis of the probe. So time reversal is able to correct along the primary axis where you have multiple elements, but it's not able to correct along the secondary axis where you only have one element, for example. Intradose or extradose of 90-degree bends is not a problem. And typically, we're going to use time reversal in an immersion environment. So there's a few examples of uses we can look at. The first one is the limitations of phased array and how you could go using phased array versus time reversal. So in this case, on the left-hand side, we have traditional phased array. And you can see that we lose signal as soon as we leave the normal of the probe with respect to the specimen. As on the right-hand side, we have the time reversal window where time reversal is applied. And you could see that up to a 15 to 20 degree misorientation of the probe with respect to the surface, we're still keeping good signal. And that really goes to show that it's able to correct for the bends that can happen along the length of a long composite surface, for example, so that using that time reversal really becomes handy when you have a surface that's not fully flat throughout the full specimen, or a little bit of a changing geometry, where you can really see how the traditional phased array is getting lost at about 3 or 4 degrees, but time reversal, we're able to go much higher than that in misorientation. And then we could look at what we can get from a corner part. So in this case, we're going to have an inspection of first the flat part of that part, and then we're going to do another pass on the bent part. So on the flat part, there's a little slight misorientation, And we're still seeing a better signal on the time reversal than we do on the traditional phased array, especially around the curve, where we're able to see right down that there's a lot of noise in the traditional phased array. So some of the flaws could be lost, or some false call could be made, and that's what we're seeing here with that blue line at the bottom, which is really near the curve of our bend, where we're not able to see flaws at all in that area with respect to that time reversal, which sees all the flaws, no problem. We're going to get all these really clean images. So that's one of the things on the flat part. But where it really comes in handy is when we're on the bend, where the non-time reversal channel, traditional phased array, has a range about 5 millimeters from each side of the zero, while the time reversal channel with the same probe has a range of about plus or minus 15 millimeters from the center. So that one saves a lot of time and gives you a much cleaner signal, where you're able to see that beam forming through the whole part, instead of having only a slight section of your image coming out. So you're going to save a few passes, or even just get indications that you wouldn't get if you weren't using time reversal. So that's another user case where it comes in really handy, because you don't have to do multiple passes. For example, you are able to collect a lot more data in a single pass, and you can also look at the sectorial that is a lot cleaner. You don't have as much noise, and you don't have the same amount of bend in your measurements. So you're actually able to read the correct values with depth, as if you're not using time reversal, since there's that bend in the interface. The depth you're going to be reading will always have to be relative to a new interface that changes, instead of being relative to zero position. That brings me to mention that Ultravision has a tool to correct for those bent parts. So you can enter your curved specimen with the correct radius, inner, outer radius, material, and things like that, and you're going to be able to directly correct for that bend in the part, so that the width of the flaws you're going to be inspecting is corrected for that particular shape. And finally, we have what we call the tiger stripe inspection. So a lot of composites have their own fibers, the way they weave the fiber in the part. And without time reversal, that's not something you're necessarily able to see. But now both gates actually show a time reversal channel, and you can see that we're able to see those what we call tiger stripes, or the direction of the strands of the carbon fiber inside the part. And that's going to allow us to see if there's a break in the pattern, for example, or if there's a flaw that shouldn't be there. And without time reversal, that's really not possible to see. But we're able to see that a lot cleaner with time reversal, where if I'm changing my palette a little bit, I can see really the direction of the strands, make sure everything's going the way it should be. The things are waving and intercutting the way they should. And that's really another advantage you have using time reversal versus a traditional phased array, where that kind of detail would get away from you. So sometimes maybe a mess in the strands could be mistaken for a flaw or something like that. So you're able to distinguish between smaller details when you're using time reversal versus using standard phased array. So overall, the benefits of time reversal, well, it's going to simplify your composite inspection by compensating for the probe misalignment or misorientation on your part. It's going to enhance flaw detection capability and porosity assessment, just by showing you a much clearer and cleaner image of your material. And it's going to reduce the cost for complex mechanical systems. So usually a simple 1 or 2 axis mechanical system instead of a 6-axis robot will be more than enough. If you're using time reversal, you're not going to have to go into a really complex and expensive mechanical systems. So I'm done with the presentation. If anyone has questions, I'm available to answer them. Just send them in the chat, and I can answer those. GP is asking, can time reversal be used on other materials other than CFRP? Yes. We're talking about CFRP here because they're the most standard ones with the complex shapes and the bands and stuff like that. But you could use it on any material you want. Really, time reversal is a technique that's going to compensate for the interface alignment. So whatever surface you're going to be using on, the material is not important as long as you get a column of water between the material and your probe, you're good to go. Victoria is asking, does time reversal have to be used in immersion? That's a good question because yes, we've talked about immersion today, but the truth is we've used time reversal, for example, with roller probes or localized immersion probes to be able to correct for some of the surface texture, for example, or surface roughness. So it does not have to be used in immersion. It has a better result using it in full immersion, but you could use it with local immersion devices and it's going to work just fine. There's no real point in using it, for example, with a solid wedge, since the wedge has a fixed delay. But if you're using either Aqualink or a localized immersion technique, it's going to work just great. Sarah's asking, what's the limitation on geometries that can be corrected? So I mentioned it briefly earlier. The hardware is able to correct for either a straight surface, so a flat surface, or a parabola. So first or second order equations can be corrected. In reality, we've seen that it also works with small texture on the top of a surface, so that can be used on there. But really, you're not going to be really able to correct for small SS shapes, for example. So the limitations are first and second order equations that can be solved. And so that means flattened curves, a single bend curve, basically. All right, so it seems we don't have any more questions, so I'm going to let you go on this. If you have any more questions, you can contact me at my email address that's written at the bottom of the screen, and I'll see you at a next coffee break.